Every year, the experts closest to quantum computing get asked how likely it is that a machine breaks RSA within 10 years. The latest edition of that survey put it between 28 and 49%, and the edition before put it at 14 to 34%. A number moving that fast is almost impossible to plan against. Your board is going to ask you when this actually happens, and whatever you answer, you'll be wrong in one of the two expensive directions. Tell them it's decades away, and you'll be the person who said it. Call it imminent, and you'll spend credibility that you'll definitely want to get back. There's a third answer, and it's the defensible one. By the end of this video, you'll know why your RSA is standing anyway, why the machine an attacker needs keeps getting smaller, and the two questions that end the argument the next time somebody puts a qubit headline in front of you. I'm Addie Lamar, founder and principal advisor of Lamar Labs, with 15 years inside the cryptography the entire digital world trusts. This channel puts you in command of the quantum transition, so you lead it while the rest of your industry is still guessing. Let's start with the assumption in most boardrooms, because it's the one that talks leaders into waiting. And that is that quantum is a science project which hasn't produced anything of value yet. In April 2026, a research team, including Germany's Federal Security Office, used a real IBM quantum machine to break a cipher called Even Mansour. It carries a formal security proof, and its structure is closely related to a single round of AES. They did it on hardware rather than in a simulation or on paper. So quantum cryptanalysis has already happened once on real hardware this year with a national security agency's name on the paper. Also, this June, I spoke at Quantum USA in Washington, D.C. on the post-quantum cryptography panel. Earlier that day, I sat in a room for the National Strategy Panel where Dr. Tanner Crowder, who runs quantum information science at the Department of Energy's Office of Science, made the point that people keep lumping all of quantum together. And it makes them wrong about all of it. He put quantum computing itself at an ENIAC moment. And the comparison really does work, because ENIAC was a genuine working computer that filled a room and did less than the phone in your pocket. The machine and results are real, but the scale is wrong. Which is the whole puzzle, and it's the one worth sitting in. A quantum computer broke a cipher this spring, but your RSA is still standing. Why? There are two completely different qubit counts in circulation, and the press only ever prints one of them. The one you've seen is likely physical qubits. Those are the actual hardware components, and they're noisy and error-prone, and today's best machines have thousands of them. That number climbs every year, and it gets reported as a countdown. The one that decides your fate is logical qubits. A logical qubit is an error-corrected qubit, and you build a single one out of many physical qubits working together to cancel out each other's mistakes. Depending on the hardware and the error correction scheme, one logical qubit can cost anywhere from hundreds to thousands of physical ones. Now put the two together. The most recent public estimate for breaking RSA 2048 comes from Google's own quantum team, and it lands at under 1 million noisy physical qubits, running for under a week. Today's best machines have thousands, so the gap is still enormous, and I want you to hold on to that. To put it into context, let's look at what that number used to be. The researcher behind that estimate, Craig Gidney, published a figure in 2019 that put the same job at 20 million qubits and taking 8 hours. In 2025, he revised his own number down to under 1 million. So that is a 20-fold cut in the size of the machine an attacker needs, and it happened without any new hardware at all. Instead, it came from better algorithms and better error correction. The requirement moved on paper. Then, in March of this year, his team did it again to elliptic-curve. Google's quantum group, working with Stanford and the Ethereum Foundation, put breaking a 256-bit elliptic-curve key at fewer than 500,000 physical qubits, running in minutes. Another 20-fold cut. And rather than publish the attack itself, they proved the claim with a zero-knowledge proof, so anyone can verify they hold circuits of that size without ever actually seeing them. So there are two numbers moving toward each other. The hardware is climbing, which is the number in the news, and the machine you would need is shrinking, which is the number in the papers. Nearly every leader I talk to is watching one of them. The gap is real. And it's also closing from both ends. So when do they meet? Once a year, a few dozen of the world's leading quantum experts are surveyed on a group of questions, but we're going to focus on one. How likely is it that a machine capable of breaking RSA 2048 exists within 10 years? That survey exists because the point where those two curves cross can't exactly be calculated. One of them is hardware, which runs on roadmaps and funding, and you have no way to audit. The other is mathematics that haven't been published yet, and nobody can put a date on discovery. That hasn't happened. So anyone who hands you a year is guessing with confidence. So the field does the only rigorous thing available. It asks the people closest to the work what they personally believe, and then it watches how their answer moves. That survey is the Quantum Threat Timeline Report, published by the Global Risk Institute and lead authored by Michelle Mosca. The most recent edition, published in March 2026, surveyed 26 experts. Their average estimate came in at between 28 and 49%. That's somewhere between roughly 1 in 4 and 1 in 2 inside a decade. And the edition before it put the same 10-year estimate at 14 to 34%. The movement is the finding. A single number from a single year tells you almost nothing, but the direction those numbers are traveling tells you what to do. So you can't really have a date, and like we discussed in another video, you probably won't ever know when it comes to exist. But what do you do with this probability? A date is technically somebody else's variable. You don't control it, can't verify it, and a program built on it rests on a forecast you never made. So here's what you do instead. The next time somebody waves a qubit headline at you, ask two questions in these words. Is that a physical qubit count or a logical one? And what year is the resource estimate you're comparing it against? The first question tells you whether the number means anything, and the answer is nearly always physical. The second one is the one almost nobody asks. If the estimate is 20 million qubits, you're being measured against a paper from 2019, and the current figure is a 20th of that. Then pull the survey yourself because it's public and annual, and no vendor needs to interpret it for you. What you walk out with is a sound probability, the direction is moving, and a program that plans against your own exposure instead of somebody else's forecast. It's free to defend because every piece of it is checkable and none depends on you being right about any date. There are 3 errors most leaders make here, and each one hands them a false reading of the clock. The first is treating RSA as the benchmark. Elliptic curve keys are far smaller than RSA keys at the same security level, so the machine that breaks elliptic curve is a smaller machine and it arrives first. Google put it at under 500,000 physical qubits against under 1 million for RSA. The half of your estate that falls earliest is the elliptic curve half, and that's the half negotiating most of your TLS. The second error is quoting the low end of the expert range as the estimate. The instinct is to carry the conservative sounding number into the board deck, but 28% is the optimistic end of that spread. Definitely not the cautious one. You plan against the top of the range because that's where the cost of being wrong actually lives. The third error is waiting for a verified quantum advantage as the starting gun. The honest counterpoint made by a speaker at that same conference is that no fully verified quantum advantage exists yet, and he's also right. It's still the wrong trigger because breaking a cipher doesn't require general advantage. The even Mansour break ran on real hardware while no one was claiming any. Both numbers are moving. So if you watch the qubit count climb, you'll feel like you have plenty of time. The number that actually sets your deadline is the one falling quietly in the papers. You can answer the timeline question in a way that survives a skeptical board now, and you can tell in one sentence whether any qubit number put in front of you actually means anything. And when you decide that turning a probability into a defensible plan is bigger than what your team has room for, that's the work I do at Lamar Labs and the links below. Which leaves you with the obvious problem. If you can't plan against their date, you have to plan against your own exposure. And that comes down to a piece of arithmetic you can run on your own data this week. Most leaders have never run it, and a lot of them get a negative number. And that's what we'll cover in the next video. I'll see you there.